Hi, this is Captain Hook number 1 for Lockpickers United, and together with the help of RPAMP, who's doing the editing and the animations in this video, I will give you a brief overview of disk detainer logs. I will not go into the higher security ones, but I will go to this guy and I will show you how this one works, and I will go into the basic disk detainer logs, which are usually the cheap Chinese ones, and yeah, maybe the intermediate kryptonite or so you will also be able to open with the knowledge that it takes to open this guy. Actually, this guy provides you more knowledge than you need for kryptonite or so. I plan to part this video in 3 parts. The first one will be briefly discussing the main functioning parts of the generic disk detainer logs, and the second part will focus on disk detainer logs with false gates. And the third part is about this log as an example of how to pick it and what knowledge can help us to pick this easier, and also a short look into the tooling we need. Okay, have fun with the following videos. So now let's have a look at how this works. We have the core, which is basically everything in this silver shell here. For example, we have these disks. They are called code disks. Everything that has the possibility to move in a certain range. So it's defined by this bump here hitting this edge and this edge. So this is the angle it can rotate. It's usually 90 degrees. Then we have some cutout here, which is called a true gate, or in the case of no false gates, which means shallower cutouts on the sides, this is just called a gate, because there are no false gates in this log here. It's a very cheap Chinese one. And we can see here's some rod, which is going down all the way along those disks. And we have a cutout in here, which the rod is fitted halfway into, and the other half of the rod sticks out of this shell and is caught up in this cutout here. So if we now want to rotate this core, we can see it's hitting this edge here and gets pressed into the shell or into the core, but those disks here prevent it from entering further. And we can already see if this gate here aligns with this cutout here, then the sidebar can enter further and we can rotate the core even more. So let's demonstrate this with a key. So I put it in here, and now you can see when I rotate the key, those gates align, and some disk right in the back here, maybe you can see it, I'll show it later again, is now putting tension on this silver shell, and we can rotate the core even more. And now the lock opened and the shackle fell out. Let's lock it back up and pull out the key. So if we now rotate one disk to its right position, like this here, all the others below are still not right, so it will not open. But for an open, we would have to turn this core. So one of those disks has the gate not here, but here. So if it's rotated all the way like this, the sidebar is allowed to enter. And if now the key tries to rotate it further, it's pushing into this edge and putting tension on the core and turning. So if we want to tension this lock, we have to find one of those disks to tension it. Usually the keys are always have one of those cuts right in the front or right in the back. There are some locks, like some kryptonites or Abus Plus, which have random tensioning. Then there's a 0 cut disk, which you can see here too. So this one here we could also use for tensioning. So because we want to have this connection here for torque, but we also want to to have the gate aligned, because if it's not, the gate can't even enter here, and we are blocking the next disks from getting feedback of this here. Because like in a pentambler lock or so, we have some friction between this bar wanting to enter the core and the disks which are blocking it. The disks are not all the same diameter, or there are some tolerance problems in the lock, like in pentambler locks. So we have not all disks binding at the same time. There's always one disk who is the most in the way. And this one we have to find, rotate it to the right part, and then it's all good. So we already could see one problem. If we want to have a tool which is shaped like this cutout, we cannot move to the next disk if this one is rotated. But there's a tiny flaw in this lock, and that's basically how it must be if it should work, because we can see those cutouts here, and each cutout is hitting a disk, and if there's like a bigger angle here, it will hit the disk later and therefore start turning it later, and also just a smaller angle. So this cutout here will be a 90-degree turn, while this cutout here will just be a 45-degree turn. So if we now have two disks of a different cut lying directly on each other, then the one would turn the other with it by friction. So we have to have these guys in between to stop this. This here is called a spacer. We can see it has some edge here which is hitting both rotation stops, so it cannot rotate, and therefore the gate is already aligned and we cannot change it here. But this allows us to have a very thin tip in our tool, which is basically rotating in between two disks. So if we now have this disk angled like this, we can stick our pick through and rotate in this space. This spacer here leaves us to turn it from this direction to this and enter the next. So this makes the need of a very thin tool. So for example, here I have made a tip which is very thin, just about the thickness of one of these spacers here. So this is one of the spacers which we want to rotate in between. So we're going in like this. In here we can move freely and orient for the next disk. This is basically everything we have to do. And now let's talk about the feedback we get. Basically, we have the sidebar hit this disk here somewhere. Let's say it's the binding disk. So this disk actually gets pushed in by the sidebar, and now it will grind along. And when we rotate it further, we have some point where we have no friction, because the sidebar tries to enter. It cannot touch the bottom already because the disk above and below are placed like this. And so the sidebar can't enter further, and therefore we have no friction here. I'll show you a nice animation of how this works and how we have some rotation if the sidebar is not entering completely. So this is basically everything you have to know how these function and how to pick them. I suggest you to also watch the end of the video where I show you how I can use this feedback to pick this ABUS Plus. Here we have another example of how the disks turn. We can see this Abloy exec, and now if I am turning the key, it will start to rotate some of those disks. You can see this is like the same angle which I showed you before, and we have the same bumps which can turn in this defined angle, and like this those are hitting, so we are already done. And now the core can turn, and we are waiting for the sidebar, which is here, flat in the core, and now we can rotate back and take the key out. Let's quickly discuss how we get the feedback from where we are on these disks here. We have our sidebar riding along here, and we have some false gates here, and a true gate here, and a false gate here. So how do we know this from outside of the log? First, let me show you this animation. Okay, now that we have seen it, let's talk about what that means. I've already put a table here which is discussing every single part or state we can have on every single disk in the log. We can have the first state is we have no binding at all. The sidebar is not even touching it yet. And this means we have actually no feedback. It feels loose, there's no friction. And this happens over the biggest part of it, or usually even over the whole part of it. Sometimes there's a tiny edge grabbing or so, but if you do not have feedback over most of the rotation angle, then we have no information really, and we just ignore it until we find the real binder and come back to it later. If we have binding and we are not on a gate, this means we have permanent friction during the rotation where we are not hitting a gate. Usually you can feel even a click if you rotate further and you're encountering a gate. Even if it's true or false, it doesn't matter. But then you have to feel for the new feedback and basically find out where you are again. So what do I do if I'm binding permanently? This means I have just to rotate so long until I hit a click. I can feel suddenly something that is frictionless also, and then I have to feel for new feedback. Now when I'm hitting a gate, let's say it's a false gate, then the sidebar usually enters it just a tiny bit, because it can't enter completely, because the disk above and below and all the others are preventing the sidebar from entering further. So first, as you can see in the animation, there is a frictionless movement over a small angle. And this means we have to ignore it, because we can't really say if it's a true or false gate. If there's no friction, it means it's not in the way of the sidebar. And this means for now, we do not have to care about it. But as you will see later in the ABAS Plus picking, there's actually a difference usually in the amount of rotation you get out of, or you get this frictionless movement. And usually it's smaller for false gates and bigger for true gates. So if we know this free rotation angle and can compare it to a true gate, then we can actually know if it's a false or true gate. And if we know it's a false gate, we can skip it and check for the next gate we find. Okay, let's say we didn't do this and we are still in a false gate, and later in the picking the sidebar can protrude further because the disks above and below are picked or also in false gates. This means the sidebar can enter the false gate completely, and now it's grinding on the ground of the false gate. In the animation you can see it, and it looks pretty similar to the part where it doesn't hit the very ground of the gate, because there's literally a very small difference only. So now we have friction in this angle, and we are hitting like rotation stops at the end. This means that at the limits we have increased resistance, and we know we are in a false gate. So we reduce tension and jump to the next gate. Of course, after we are out of the false gate we were in initially, we will apply tension again, and so we can feel when we are hitting the next gate. Okay, so much about false gates. What happens if we hit a true gate? First, it doesn't really move different from a false gate with the sidebar not fully entering the bottom. So we have a frictionless movement over a certain angle. This is often bigger than false gates, but it does not have to be. For example, Abloy or so, they are playing with it. There are bigger and smaller false gates, but a true gate will always feel frictionless. If there's friction, it's not a true gate. So we leave it in that position and try to apply tension during we move between the disks to the next one, so we do not disturb or turn this disk unwantedly. Now what happens if the sidebar enters the true gate completely? Well, there's actually still some play, because it will never hit the very bottom and be pressed against it, because otherwise we would have such a crazy precision that it will grind off and we will get this frictionless small amount of rotation angle again. Yeah, that doesn't have to make sense, but it still moves a tiny bit. If you can feel every disk in the lock be on some part where there's frictionless movement, and the lock still does not open. There's basically only two possibilities. First, you're wrong and you should apply a bit more tension and check the disks again if they are binding or not. Sometimes there's like loop or grease and you just don't really feel it, but if you increase the tension just a tiny bit, you can feel it much better and find that some of those disks which was seemingly jiggling, that's how it calls to rotate it in this small part, or rotation angle, or it's just that the locking mechanism is greased and you need just a bit more tension to finally unlock the lock. Okay, so this is a very, very complete table, I guess. It's maybe a bit too detailed, but that's all you need to know about the feedback, in my opinion. For gutting, it's important that you know how to get this retainer plate unscrewed. So first we have to get all the discs oriented back again by doing this. Now the lock opens and we have some Allen screw in here which is holding two ball bearings in there. But I already took them out, so I can just thumb turn it out. By the way, if you want to drill this lock, it's bad to do it through this way, because here we have a so-called spinner disc. It's a gateless disc which is rotating freely, and this should protect it against drilling. But if you drill out here a big enough part, like 4 millimeters deep, you can drill out the screws, the balls which are retaining this guy here. So that's basically a very cheap way to get this drilled out. So now here we can see the groove, the actuating mechanism in the back, which is interacting with this part here, and we can see that the sidebar is sticking out. And if I put in the key, rotate it, then it can fall in and is flush with all the other discs. So let's get this guy just partly apart. Oh no, I have to get everything out to show you the last disc, which is the reason why this does not back tension. Here the limiting is not made by some bump, it's made by this cutout here, and here we have some small edge on the inside which the discs are hitting on, so like this, and we can see the true gate is aligning with this sidebar groove, so this is actually a tensioning disc. If we look closer at the disc, you can see that there are some false gates on it too. And so now we have the true gate, which is very wide here. Oh no, what a pity, this one doesn't even have any gates, any false gates, but this guy does. So here we have the true gate, which is pretty wide, and we have some smaller false gates here. This is what we could feel as a smaller angle as this here. And here we have another false gate. And we also can see what cut it is. It's a number 4 disc. Yes, this is basically all the same for the other locks or the other discs, which we can see here. All their true gates aligned, and now some false gates and how late they rotate. So basically when I now turn the key, the first discs that turn are the higher cuts and the later discs are the lower cuts, because they hit these edges here later after a certain amount of rotation. So let's get this out. Because of the numbers on the discs, I do not have to worry about the order they had. It's easy to find out later. And now we can see the last disc in here, which is called a butterfly disc. This here is actually not made for tensioning, because if I put it in here and turn it, let me go to autofocus, and like this, how it is. So if I now turn this guy until the edge is hitting this here, you can see the gate is already misaligned. So it's turned too far. And if I rotate tension back, this gate aligns, and then I have to tension with the second last disc the second last disc, which is not this butterfly, to tension the lock, which I will show you later in the picking of this lock. So this is the butterfly disc and the true gate it has and the core. Okay. So here's the ABUS 8950, which I just showed you the guts of, and now I will show you how it gets picked, so you understand what I'm talking about all the time. So first, it's not necessary, but it's probably a good habit. You can take, for example, some of those dimple tensioners and just rotate all the discs clockwise or in the opening direction. There are also locks which open anti-clockwise, but I think it's not so common, probably. Not sure on that. So then I have here a silver bullet, which is consisting out of these lines here and here. And if we look closely, those here are much tighter than these here. So these here are spaced 2 millimeters, which is exactly the distance between two coat discs. So basically the thickness of a disc and a spacer together is 2 millimeters. Whereas in many alloys, it's just 1.6 millimeters. So we have this scale here. And we also have some gate numbers here, but for the picking of this lock now, I will not take it into account. I will just look at the spacing or at the amount of rotation I will get as feedback. So now that I have everything oriented, it's much easier to have the right table facing towards me, because I do not have to turn the tensioner so much anymore. So we just drop this in, and I will put some better focus for you. So let's focus it like this. And now when I apply tension, I can see here on which disc I'm on. So here we have a spinner disc as the very first. Then I can drop below, and I'm here. And I already know, because it's an old ABUS Plus, that there's a 6 cut here. So this lock could actually front tension. But if I would front tension it, I couldn't show you the cool back tensioning technique for the random tensioning attack. So we know there's already a tensioning disc in the front, but we will not use this for tension. We will use the last one. And if we already look at the amount of play I have, so from here to here, this is the play I have. We can see I'm skipping this indexer in the middle, and I'm almost getting to the other two. So this much. This is the width of a true gate. So now if I go down to the next one and I do the same, I will get a strange feedback, which is like from this guy to this guy. So this means here's a false gate because it's not the full width. And if I turn further, I hit something that doesn't want to let me rotate further. But if I remove tension, because in this lock I can drop off tension whenever I want, there's no spring or nothing will drop. So, or that's generally in this detainer. So this was the sidebar getting caught on the last disc. So now let's start again. Now we are here at the first disc. We can see true gate. Next disc, we have this feedback, which is slightly asymmetric. So let's go to the next cut. So here we already have like a very big movement. We can see here it's really hitting both of those indexers. So let's go to the disk below. Now we are on the spacer in between. Here we can rotate freely. So I'll go on here and turn until I can drop into the next disk. And if it doesn't want to, I have to play with the angle here, because if the angle is off, it's quite hard to hit the next gate. So let me just get some orientation back, and now we are on the next disk. So here is a very small amount, and now here I can feel friction because I'm not even in a gate. Let's keep turning. Small amount, false gate. This here is a bit more, but let's see what else is there. There's this huge part here, and after it there's friction, and we're already done. So we know this here is the true gate. Let's go down, find the next hole here. There's nothing, friction, friction, false gate, further. It's a little bit bigger maybe, but still not too big. This here is again very big, so it's probably a true gate. Let's continue. So where am I? It's a bit hard to do it through the camera, but so here's the next disk. And here we already hit a very big rotation. Let's just compare it. Yeah, it's already this guy here. Next one. Same here. So so here we already have very big play, so no need to move him. So we know he's already a tensioning disk because he's also already turned the whole way in the tensioning direction. And now here there's nothing. Turn further, here's something, false gate. Now here I do not have much friction, and this is because so this here is not a whole true gate or so, maybe master king, I don't know. This is because the last disk we're tensioning from is not really meant for tensioning. So it's slightly blocking this guy here a bit, and I cannot get good feedback. So I will just guess some number here and memorize it. So I'll just turn it all the way this direction, go up to the tensioning disk here. Now I'll apply tension with this guy, rotate back with the former tensioning bar, and nothing happened. So I'll rotate back, go down to this guy, and I'll just increase it by one step, go back, and try again. And I do this as so long until it opens. So let's rotate back. Tension the tensioning rod and applying tension through the picking tip. So, and now something happened. I think I slipped. So let's do it again. So tension, yeah, and now it opened. So I just slipped off when it opened. So yeah, so this is how you pick the lock, by knowing that the amount of rotation you have from this disk is referring to the true or false gate you're on. So, and to get the whole pick back out, you have to close the lock. Then you can close it again and just turn out your picking tip and the tensioner. So picking tip is out, and tensioner I get out by just rotating back and forth until it comes out. So now the spinner disc is a bit in the way. Still. So now I just did this and pulled it out. So if I now could get you interested in disk detainer locks, and especially the high security ones, maybe we could also start a series about tool making and what specialties these locks have. For example, the alloy evolution line. So we have the classic, the profile, the high profile, the exec, the sentry, the disk clock and disk clock pro, the cento, the noble, and the protect 2, and also the protect, which is missing in here. So there's a huge amount of information on all these logs and what they have invented against picking, and it's very interesting. There's also tool making, which is just painful for those logs, but it's really fun if you have finally a working tool. So maybe that's something that we could go for and make a series on high security disk detainer picking. If you're interested, let me know in the comments.